Imagine rewinding a dashcam for 10 million years and discovering that every intersection, every turn, every road you check leads nowhere. That's what happened when astronomers tried to trace the third interstellar visitor ever found. 3I Atlas streaked into view in July 2025, and within weeks, teams around the world pointed Hubble, James Webb and ground telescopes at it. The orbital traceback should have been routine. Find the star that kicked it out, map the gravitational history, close the case. Instead, they found a void. No meaningful encounter in 10 million years of searching. The chemistry is bizarre. The dust behaves like nothing we've catalogued, and its motion suggests it's been drifting since before our sun ignited. Stay until the end, because we're going to walk through why this object terrifies origin scientists and what it means when an interstellar visitor refuses to answer the most important question of all, where it actually came from. Part 1. 3I Atlas is a ghost. First, let's set the scene, because what follows will blow your mind. On July 1st, 2025, the Asteroid Terrestrial Impact Last Alert System station in Chile caught something streaking through the inner solar system. Within hours, astronomers realized they were looking at only the third confirmed interstellar object to visit our neighborhood. They called it 3I Atlas, although for the remainder of tonight's journey, we'll simply refer to it as Atlas. Back to our astronomers. They pointed every major telescope on Earth and in orbit at it. Hubble, James Webb, ground observatories across the globe, and then they tried to do what astronomers always do when they find a wanderer. They tried to trace it home. Here's where it gets strange. A team led by Perez Couto published a study in 2025 that should have been routine. They wanted to rewind the cosmic dashcam, so to speak. Track Atlas's path backward through space and time to find which star kicked it out into the void. They used Gaia Data Release 3, the most precise stellar census we've ever compiled. Millions of stars mapped in 6 dimensions: position, motion, everything. They ran their simulations back 10 million years, testing Atlas's trajectory against every nearby star in the database. The search cone covered 500 parsecs, roughly 1,600 light-years. That's a massive volume of space. They flagged 93 candidate encounters, stars that might have come close enough to gravitationally nudge Atlas onto its current path. Every single one came up empty. Not a single meaningful perturbation. The closest relevant star, catalogued as Gaia DR 36863591389529611264, passed Atlas at about 0.30 parsecs. That's roughly 98,000 astronomical units if you're counting. The relative speed between them, 35 kilometers per second. Fast. But here's the problem. When you calculate the gravitational impulse from that flyby, the velocity change imparted to Atlas would be roughly 5 times 10 to the -4th meters per second. That's 0.5 millimeter per second. Orders of magnitude too small to explain how Atlas ended up on its current trajectory. It's not even close. So let me state the paradox as simply as I can. Atlas has a hyperbolic orbit, meaning it came from outside the solar system. That's not in question. Interstellar objects don't just materialize, they have to come from somewhere. But when we look for that somewhere, we find nothing. No gravitational fingerprint, no parent star, no stellar sibling. It's a cosmic orphan in every dataset we have. And before you think this is just a case of insufficient data, understand that the team ran their searches with Monte Carlo, sampling of orbital uncertainties, covariance ellipsoids, the works. They accounted for measurement, error. They checked different reference frames. They cross-referenced with other traceback studies. The answer kept coming back the same: no origin. Now, here's something interesting that keeps this from spiraling into pure mystery. Despite having a large peculiar velocity relative to the local standard of rest, Atlas is kinematically consistent with the galactic thin disk. When you plot its motion in galactic coordinates, run Tumor diagrams and likelihood diagnostics, it looks like it belongs to the population of relatively young stars that make up most of our neighborhood. It's not some halo interloper from the ancient outskirts. It's moving like something that should be from around here. But if it's from around here, why can't we find where? The discovery itself became a global campaign almost instantly. Atlas Chile spotted it. Then Hubble locked on. James Webb turned its infrared eye toward it. Ground-based observatories from Hawaii to South Africa tracked it nightly. This wasn't some faint smudge barely visible in one dataset. Atlas became one of the most intensely observed objects in the sky almost overnight, and yet, for all that attention, for all that data, we still can't answer the most basic question you'd ask about any object. Where did you come from? I want you to understand what untraceable actually means here. This isn't scientists shrugging and saying we don't know yet. This is scientists saying we looked for the trail and there isn't one, at least not in any catalogue or method we currently have. Imagine you're watching a dashcam video. Someone tells you to rewind it and find the last turn the car made. So you rewind 10 seconds, a minute, an hour. But as you go back further, the roads start to blur, intersections smear into each other, lane markings dissolve into noise. By the time you've rewound 10 million years, the car is still on the road, but every intersection you check, every exit ramp you examine, none of them are where the car came from. The trail simply vanishes into chaos. For the field of interstellar object science, this is more than just an interesting puzzle. If Atlas can't be linked to a parent system, then the entire program of mapping galactic chemical evolution through these wandering rocks hits a wall. The idea was elegant. Catch an interstellar comet, analyze its composition, trace its orbit back to a star, use the star's age and metallicity to date the comet's formation. Do this for dozens of interstellar visitors, and you build a chemical map of planetary systems across the galaxy. But if the very first step, the orbital traceback, fails for reasons we don't fully understand, then what? I should add a note of caution here. Untraceable does not mean untraceable forever. It means untraceable with present catalogues and present methods. Future releases of Gaia data might fill in gaps. More precise astrometry could tighten the orbital uncertainties. New proper motion catalogues for fainter stars might reveal a parent we're currently missing. The universe doesn't hide its secrets out of malice. It hides them because we haven't built good enough eyes yet. But right now, today, with the best data we have, Atlas has no traceable ancestry. And that's unsettling in a way that goes beyond mere ignorance. So if we can't trace where it came from dynamically, can we at least infer its birthplace from what it's made of? That's the next move. If orbital mechanics won't talk, maybe chemistry will. Because when James Webb pointed its spectrograph at Atlas in August of 2025, what it saw was downright bizarre. The gas pouring off this thing, the coma, the cloud of sublimating ice, it's not what comets are supposed to look like. Not even close. Part 2. The Failed Ancestry Search. Let me walk you through exactly how the hunt for Atlas's parent star played out, because this isn't some vague hand-waving exercise. This is a forensic investigation with millions of suspects and a timeline stretching back to when our ancestors were still figuring out stone tools. The method reads like a procedural crime drama, only the crime scene is 10 million years deep, and the suspects are stars. Step 1. Perez Couto and their team pulled the Gaia data release 3 high-quality 6-dimensional stellar catalogue. That's not just positions of stars on the sky. That's positions, proper motions in 2 directions, parallaxes for distance, and radial velocities for motion toward or away from us. 6 numbers per star. They filtered for quality. Parallax greater than 2 milliarc seconds to keep nearby stars. RUA, the renormalized unit weight error, less than 1.4 to ensure the astrometry is clean. At least 8 visibility periods to avoid flukes. After all those cuts, they had 3.6 million stars with full radial velocity data. 3.6 million potential parents. Step 2. Initial conditions. Before you can rewind anything, you need to know exactly where it is now and how fast it's moving. They used the pre-entry heliocentric state vector, calculated by De La Fuente Marcos and colleagues in 2025. Heliocentric means measured from the Sun's perspective. But to integrate orbits through the galaxy, you need to convert that to galactocentric coordinates, measured from the galactic center. That conversion requires knowing the Sun's motion relative to the local standard of rest, the average velocity of stars in our neighborhood. Get that wrong, and your whole traceback shifts. They didn't get it wrong. Step 3. Choose your gravitational potential. The Milky Way isn't a point mass. It's a swirling disk of stars, a bulge of old stars at the center, a halo of dark matter wrapping the whole thing. To integrate orbits accurately, you need a model that captures all of that. They used MW Potential 2022, a state-of-the-art galactic potential model. They used a package called Gala to run the integrations. 10 million years back, step by step calculating the gravitational tug of the galaxy on Atlas and on every candidate star. Now here's where it gets tricky. Orbital uncertainties. We don't know Atlas's position and velocity with infinite precision. Small errors today become enormous errors 10 million years ago. So they didn't just run one integration, they sampled from the covariance ellipsoids of the orbit, running Monte Carlo draws. Hundreds of slightly different versions of Atlas's trajectory, each one consistent with the observational uncertainties. If any of those trajectories produced a close encounter with a star, that star would be flagged. But here's the kicker. Even with generous Monte Carlo sampling, even with uncertainties blown up to account for chaos, not a single flyby turned into a plausible parent. Let me give you the headline numbers: 93 nominal encounters within 2 parsecs. Of those, 62 passed at least a 2 sigma significance threshold. Sounds promising, right? 93 chances to find a parent, but when you calculate the actual energy exchange, the delta V imparted by each encounter, they're all negligible. The strongest one, that Gaia star I mentioned earlier, gives a velocity change of about 5 times 10 to the -4th meters per second. That's nothing. For context, a human walking imparts more momentum to the air molecules around them. This is a non-event, gravitationally speaking. Why is 0.30 parsecs at 35 kilometers per second a non-event? Because tidal forces scale inversely with distance and directly with relative velocity. When two objects are moving fast relative to each other, the gravitational interaction is brief. There's no time for momentum to accumulate. You can think of it like this. Imagine trying to grab a baseball while riding past it on a motorcycle at highway speed. Your hand is near the ball for only a fraction of a second. You're not going to impart much force. That's what's happening here. Only the motorcycle is a star, and the baseball is Atlas, and the highway is the Milky Way. Other teams have run similar studies. Go and colleagues in 2025 used slightly different initial conditions, applied different parallax systematics corrections, and ended up with different encounter tallies. Their numbers don't perfectly match Perez-Couto's. But, and this is crucial, the bottom line is the same. No smoking gun parent, no flyby that could plausibly explain Atlas's trajectory. The discrepancies are in the details, not the conclusion. When you reconcile the differences, accounting for reference frame choices and covariance sampling, the story stays consistent. Atlas is an orphan. Why stop at 10 million years? Why not go back further? 2 reasons. First, chaos. Stellar orbits and interstellar object orbits diverge exponentially over time due to tiny perturbations. The further back you go, the less meaningful the integrations become. You're not tracking real history anymore. You're tracking noise. Second, catalogue limitations. Gaia's radial velocity measurements get sparse beyond about 500 parsecs. Most stars in the galaxy don't have measured radial velocities at all, so even if Atlas came from a star 2 kiloparsecs away, we wouldn't have the data to check. 10 million years is the practical ceiling where traceback still has a chance of being scientifically meaningful. Beyond that, you're just fishing in the dark. So what does it mean that Atlas is kinematically consistent with the galactic thin disk? It means that when you look at its motion through the galaxy, its U, V, W velocity components, they fall within the distribution typical of relatively young disk stars. It's not moving like a halo star, which would have a highly eccentric inclined orbit and much higher velocity relative to the local standard of rest. But here's what it doesn't mean. It doesn't uniquely tell you Atlas's age or metallicity. Thin disk membership is a statistical statement, not a biography. It rules out exotic options, like Atlas being an intergalactic traveller or a halo relic. But it doesn't pinpoint a formation environment. So we've hit a wall with dynamics. The orbital traceback, the tool that should tell us where Atlas came from, gives us nothing. We've looked as far back as we can with the data we have. We've checked millions of stars. We've accounted for uncertainties, and the trail is cold. But maybe, just maybe, the object itself can tell us something its motion can't. Because Atlas isn't just a silent rock, it's active, it's outgassing, it's wrapped in a coma of sublimating ice and dust. And when James Webb looked at that coma, it saw something that doesn't fit any pattern we know. The gas pouring off Atlas is bonkers. Part 3, the CO2 coma paradox. On August 6, 2025, the James Webb Space Telescope turned its near-infrared spectrograph toward 3I. The object was about 3.32 astronomical units from the Sun, just inside the orbit of Jupiter. Webb captured an integral field unit spectrum of the coma, the cloud of gas and dust surrounding the nucleus. What it found was a carbon dioxide-dominated coma. The 4.3 micron Nu3CO2 band was strong, unmistakable. There was also water, carbon monoxide, tentative detections of carbonyl sulfide, plus water ice absorption features and dust. But the standout was CO2. Lots and lots of CO2. Let me give you a number that makes this weird. The mixing ratio, the abundance of CO2 relative to water, came in at about 7.6 plus or minus 0.3. That's among the highest CO2 to water ratios ever measured in any comet. For context, most long-period comets and Jupiter family comets have CO2 to water ratios well below 1. Water dominates. CO2 is a trace component. But Atlas flips that script. CO2 is the dominant volatile with water taking a backseat. The only other comet that comes close to this is C/2016 R2, Comet Pan-Nadars, which also showed unusually high CO2. But even that was an outlier in a dataset of hundreds. Atlas is joining a very exclusive, very strange club. The morphology of the coma adds another layer. Webb saw enhanced outgassing on the sunward side, which makes sense. Sunlight heats the surface, ice sublimes, gas vents preferentially toward the sun. But here's the odd part. Despite this clear activity, despite visible asymmetry in the coma, there's no strong signature of non-gravitational acceleration in Atlas's orbit. I'll get to that in more detail later, but file it away. Active coma, no detectable rocket effect, that's unusual. So what does a CO2-rich coma tell us about where this thing formed? Carbon dioxide ice has a frost line farther from the sun than water ice. In a protoplanetary disk, the CO2 ice line is typically beyond the water ice line because CO2 is more volatile. It sublimates at lower temperatures. If Atlas is rich in CO2, it likely formed in a colder region of its parent system, beyond the CO2 frost line, or it underwent some kind of processing that depleted surface water while preserving CO2. There are two natural pictures, and they're not mutually exclusive. Picture 1. Atlas has an intrinsically CO2-rich nucleus. Maybe it formed in the outer reaches of a planetary system where CO2 ice was abundant. Maybe its surface has been radiation processed over millions or billions of years, converting water ice into more complex organics and leaving CO2 behind. Maybe there's a mantle, an insulating layer of dust and refractory material that's kept water ice locked deep inside while CO2, being more volatile, can still escape. Picture 2. Poor thermal wave penetration. At 3 to 4 astronomical units, sunlight might not be heating the nucleus deeply enough to reach buried water ice. CO2, with its lower sublimation temperature, can vent from a shallower layer, giving the appearance of a CO2-dominated coma, even if the bulk composition has more water. When Atlas gets closer to the Sun at perihelion, around 1.36 to 1.4 AU, we should see water turn on. If the ratio drops, picture 2 wins. If it stays high, picture 1 looks better. Compare this to the other famous interstellar visitor, 2 I/Borisov. That object, which passed through in 2019, was CO-rich, not CO2-rich. It looked a lot like solar system comets in many ways, just with a bit more carbon monoxide. Atlas's CO2 skew is new territory. It's not following the same chemical playbook. That suggests a different formation environment, a different thermal history, or both. And that's exciting because if every interstellar object we find has a different chemical fingerprint, we're sampling a diversity of planetary systems across the galaxy. But it also makes it harder to build a unified picture of what interstellar objects are supposed to look like. What should we watch for at perihelion? Atlas will reach its closest point to the Sun around October 29th to 30th, 2025 at roughly 1.36 to 1.4 astronomical units. That's inside Earth's orbit, though not by much. If water ice is buried under a CO2-rich layer and just hasn't been warm enough to sublimate yet, perihelion should change things. Sunlight will penetrate deeper, water should start venting. If that happens, the CO2 to water ratio should drop dramatically. If it doesn't, if CO2 stays dominant even at perihelion, then we're looking at something with a genuinely unusual composition, not just a thermal effect. Now, I'm going to float some speculative ideas, and I need to be clear these are ideas, not consensus. They're interesting thought experiments, not verified science. Could Atlas have formed in a carbon-rich disk around an older star? Could it have condensed in a postnova cloud enriched in CO2? Could it come from a red dwarf system where the snowline is much closer in and volatile chemistry is skewed? All of those are plausible in the abstract, but current data don't pick a winner. We don't have isotope ratios, we don't have deuterium to hydrogen or carbon-13 to carbon-12 measurements that would fingerprint the formation environment. We just have a CO2-rich coma and no parent star, so we're left with chemistry as a breadcrumb, a clue, but not a solution. Here's the kicker. If we combine the chemistry with the kinematics, the thin disk-consistent motion, we can start to triangulate an origin we can't dynamically trace. Thin disk suggests a relatively young, metal-rich environment. CO2 dominance suggests cold formation conditions. Put those together and you get something like a distant Kuiper Belt analogue in another star system, possibly with a different volatile mix than ours. That's not a definitive answer, but it's a framework. And it's more than we had before Webb looked. The coma is strange, yes, but it's not the only strange thing, because when astronomers pointed polarimeters at 3i, when they measured how light scatters off the dust grains in the coma, they found something that doesn't just look odd compared to other comets. It looks unlike anything we've seen anywhere in the solar system. The dust around Atlas is doing something that dust isn't supposed to do. Part 4. The polarization anomaly. Polarimetry is one of those techniques that sounds esoteric until you realize how powerful it is. When sunlight hits dust grains, it scatters. Some of that scattered light becomes polarized, meaning the electric field oscillates preferentially in one direction, rather than being randomly oriented. The degree of polarization, and how it changes with the angle between the sun, the dust, and the observer tells you about the dust's physical properties. Grain size, shape, porosity, composition, all of it leaves a signature in the polarization curve. For decades, astronomers have measured polarization from asteroids and comets, building up a library of what normal solar system dust looks like. Atlas does not look normal. Early polarimetry observations from the Very Large Telescope, the Nordic Optical Telescope, and the Roshan Observatory, taken at phase angles between 7.7 and 22.4 degrees, found a deep, narrow negative polarization branch. Let me unpack that. Negative polarization means the polarization dips below zero at small phase angles, a phenomenon seen in some solar system bodies but usually shallow and broad. Atlas's negative branch hits a minimum of about negative 2.7% at roughly 7 degrees. It inverts, crosses back to positive, around 17 degrees. That combination, deep and narrow, is unprecedented. We've never seen it in any comet. We've never seen it in any asteroid. We didn't even see it in 2I/Borisov, the previous interstellar comet. Why is that weird? Let me put it in plain terms. When light scatters off dust near backscattering angles, the angles close to the line between the sun and the observer, you expect some weird effects. Coherent backscatter, shadow hiding. These can produce a dip in polarization below zero, but the depth and width of that dip depend on the dust grain properties. Fluffy aggregates, loose collections of tiny monomers, tend to produce shallower, broader negative branches. Compact grains produce different curves. Porosity matters. Coatings of organics or ice matter. Atlas's polarization curve is screaming that its dust has a microstructure we're not used to seeing. So what could produce a deep, narrow negative branch? Here's the menu of possibilities. Fluffy aggregates with a very specific size distribution. Compact grains with unusual refractive indices. Grains with high porosity but organized in fractal clusters. Coatings of ice or organics that change the scattering properties. Possibly even magnetic inclusions affecting how the grains aggregate in the coma, though that's more speculative. The point is, multiple combinations of physical parameters can produce similar polarization signatures, so you can't uniquely solve for the grain structure from polarization alone. But you can rule things out. And whatever Atlas's dust is, it's not the standard fluffy aggregate model that works for most comets. Cross-checking with other data helps. Spectroscopy from Webb showed water ice absorption features. That's consistent with icy grains. Color measurements, extrapolating to small phase angles, suggest a red surface, similar to some trans-Neptunian objects and centaurs like Pholus. Red surfaces often mean organics or irradiated ices, so you start to build a picture. Red dust, icy grains, unusual polarization. Put it together, and Atlas's dust might be telling us about grain, growth and coagulation in a different environment, a planetary system with different conditions than ours. Now, I'm going to mention something that's been floating around in conference chatter and blog posts, and I need to be very clear about this. Some people have speculated about engineered microstructure, the idea that the polarization signature could be, in principle, designed. That if you wanted to create a specific scattering pattern, you could engineer dust grains with the right size, shape, and composition to produce it. I want to say unequivocally there is no peer-reviewed evidence for that. None. It's a fringe idea, a what-if story beat, not a scientific claim. We include it here because part of what makes Atlas fascinating is how it pushes us to think about what's possible, not just what's probable. But let's be honest. The overwhelmingly likely explanation is natural dust with unusual but natural properties. What this does imply scientifically, and this is the exciting part, is that Atlas's dust may probe different coagulation regimes in other star systems. Dust growth in protoplanetary disks depends on temperature, pressure, composition, turbulence, all sorts of environmental factors. If those factors are different in Atlas's birth system, the dust that formed there might have different properties than solar system dust. That's not exotic. That's just physics playing out in a different sandbox. And that's genuinely interesting because it means every interstellar visitor could teach us about planet formation conditions we can't study any other way. The negative polarization branch also matters for physical modeling. When you try to fit scattering models to the data, you have to account for single scattering versus multiple scattering. You have to choose complex refractive indices. You have to decide on size distributions. Atlas's data constrain those choices in ways that are challenging existing models. Some teams are working on fractal aggregate models with specific monomer sizes. Others are exploring coated sphere models. The point is, Atlas is stress testing our understanding of light scattering in ways that will improve the models for everything else. What should we watch for post-perihelion? As Atlas moves to smaller phase angles relative to Earth, we'll get more polarization measurements. Does the negative branch shift? Does the inversion angle evolve? Do we see hysteresis, meaning the outbound curve differs from the inbound curve? Each of those would tell us something about how the dust is changing as the comet gets more active. And if we're very lucky, we might get high-cadence polarimetry that can look for time variability, which would hint at spin state or jet activity. Polarization tells us the dust is weird. But dust is just the exhaust. What about the engine? What about the forces acting on Atlas itself? Because here's something that should be ringing alarm bells. Atlas has an active coma. It's venting gas and dust. And yet, despite all that activity, we haven't detected the one thing we'd expect to see. We haven't seen it accelerate. Part 5. The missing acceleration. Let's talk about Oumuamua for a second. When 1I, the first confirmed interstellar visitor, passed through in 2017, it caused a firestorm. Not because it was interstellar, though that was exciting, but because its trajectory deviated from a purely gravitational path. It accelerated. Not by much, but measurably. The acceleration was consistent with outgassing, a rocket effect from sublimating ice pushing the object off course. But here's the thing, Oumuamua didn't have a visible coma. No gas, no dust, at least none that we could detect. So an acceleration without visible activity sparked all kinds of speculation. Some of it scientific, exploring low albedo ice or other exotic volatiles. Some of it less scientific, invoking light sails and alien probes. Contrast that with 2I/Borisov. Borisov had a coma, a big, obvious, well-behaved cometary coma, and it had non-gravitational acceleration. Exactly what you'd expect. Gas vents, momentum transfers to the nucleus, orbit changes, textbook comet physics. Borisov was boring in the best possible way. It confirmed that interstellar comets can look and act like solar system comets. Now look at 3I. Active coma. Check. CO2, venting, check. Dust production, check. Non-gravitational acceleration detected in the astrometry? No, not as of the latest fits. That's strange. When you have outgassing, you expect a rocket effect. The gas carries momentum. As it leaves the surface, it pushes back on the nucleus. That push changes the orbit, usually in predictable ways characterized by parameters called A1, A2, and A3 in the standard non-gravitational force model. We're not seeing those terms in Atlas's orbit, at least not yet. Why not? A few possibilities. First, geometry. If the jets are distributed symmetrically around the nucleus, the forces can cancel out. Imagine tiny thrusters firing in all directions. Net push? 0. That's possible if the nucleus is tumbling or if the sublimation is coming from multiple active areas that balance each other out. Second, spin state. If Atlas is rotating in a way that averages out the jet directions over an orbit, the net acceleration could be below detection limits. Third, mass. A bigger, more massive nucleus dilutes the effect of any given jet. Hubble's upper limit on the nucleus size is about 5.6 kilometers. If Atlas is on the larger end of that range and if it's dense, the non-gravitational forces might be there but just too small to measure yet. Fourth, and this is where it gets interesting, CO2 versus water, Webb's or CO2 dominating at 3.3 AU. CO2 sublimates more symmetrically than water because it's more volatile. It doesn't need focused sunlight to vent. Water, on the other hand, tends to create more directional jets, especially from localized active areas. If Atlas's activity at this distance is mostly CO2, and if that CO2 is venting relatively evenly, that could explain the lack of a strong non-gravitational signal. The test will come at perihelion. If water turns on and starts venting asymmetrically, we should see A1 and A2 terms appear in the orbit fits. Let me float something speculative here, and I'm labeling this clearly as a narrative device, not a scientific claim. The phrase inertial damping gets thrown around in science fiction. The idea that some mechanism suppresses acceleration keeps an object stable. Could 3I, with its dense, insulated surface and symmetric CO2 venting, produce the appearance of controlled stability? Could it look to an outside observer like something that's resisting the usual cometary chaos? The answer is almost certainly no. Natural processes explain what we're seeing just fine, but the fact that the question can even be asked, the fact that Atlas's behavior is unusual enough to make people wonder, that's telling. What should we watch for at perihelion? If water ramps up and jets become asymmetric, we should start seeing non-gravitational terms in the astrometric fits. If those terms appear and are consistent with cometary outgassing, great. Mystery solved. If they don't appear, if Atlas continues to show activity without measurable acceleration, then we're in truly weird territory. That would imply either a very specific spin geometry configuration or something about the nuclear structure that we don't fully understand. Why does this matter for practical reasons? If Atlas's trajectory is predictable, if it's not subject to large non-gravitational perturbations, then planning interception missions becomes easier. You don't have to worry about the target dodging you. That sounds trivial, but it's not. Mission designers need to know where an object will be years in advance. Unpredictable comets are bad targets. Stable, predictable interstellar visitors are prime candidates for flybys or even sample return missions in the future. So we've got an object that's chemically weird, optically weird, and dynamically weird. But there's another layer to this, one that edges into the realm of coincidence and geometry. Because when you plot where Atlas came from on the sky, when you look at its radiant, the direction it was travelling before the sun's gravity bent its path, something makes people nervous. Not scientists necessarily. Scientists understand selection effects and statistics. But people, the public, the bloggers, the ones who see patterns and wonder if patterns mean something. So let's talk about the geometry of coincidence. Part 6. The geometry of coincidence. Every interstellar object has a radiant, a point on the sky from which it appears to be coming before the sun's gravity curves its path. Think of it like a reverse vanishing point. If you could stand outside the solar system and watch Atlas approach, you'd see it coming from a specific direction in space. That direction, projected onto the celestial sphere, is the radiant. For 3I, the radiant sits in a particular region relative to the galactic plane and the solar apex, the direction the sun is moving through the local standard of rest. Here's what the models say. The Otautahi-Oxford model, a population synthesis of interstellar objects ejected from planetary systems, predicts that we should see ISOs with a range of speeds and radiants. Most come from disk stars, stars like the Sun orbiting in the galactic plane. But because planetary ejection is chaotic, because stellar encounters and planet-planet scattering can kick objects out at high speeds, there's a high-velocity tail in the distribution. Atlas's speed, about 58 kilometers per second relative to the Sun, and its radiant direction fall within the expectations for ejected ISOs from disk stars. It's not an outlier according to the models. It's unusual, yes, but within the predicted range. Perez-Couto's kinematic diagnostics agree. Atlas is thin disk consistent despite its large peculiar velocity. The confusion comes from the phrase peculiar velocity. It sounds exotic, like the object is doing something it shouldn't. But peculiar velocity just means velocity relative to the local standard of rest. It's a technical term, not a judgment. Old stars have large peculiar velocities because they've been gravitationally kicked around over billions of years. Atlas's motion is consistent with that. It's not a thick disk star, not a halo interloper. It's a disk object with a history of gravitational stirring. So why do people talk about alignment? Why do blogs and forum posts breathlessly mention solar apex coincidences or planetary approach geometries? Because humans are pattern-seeking machines. We see Atlas passing relatively close to Mars, within about 29 to 30 million kilometers, and we think that's precise. We see it arriving from a certain direction, and we overlay that with Earth's orbit or Jupiter's orbit, or the trajectory of the Voyager spacecraft, and we see lines on a map that look intentional. But here's the thing, maps lie. Not intentionally, but by projection. When you flatten three-dimensional space onto a two-dimensional sky chart, things that are nowhere near each other can look aligned. And when you don't account for the volume of space surveyed and the density of survey pointings, you can convince yourself that any random trajectory is special. Selection effects are brutal. Survey telescopes don't scan the whole sky uniformly. They have footprints, areas they cover more frequently and more deeply. Atlas, the survey that found 3I, has a particular coverage pattern optimized for finding near-Earth asteroids. If your survey preferentially looks in certain directions at certain times, you're more likely to find objects coming from those directions. That doesn't mean the objects are clustering there. It means your search is clustering there. Galactic substructure adds another layer. Moving groups, stellar streams, regions of recent star formation, all of those create inhomogeneities in the distribution of potential isoparent stars. If Atlas came from a region that happens to be underpopulated in our survey volume, it'll look more isolated than it really is. The models predict this. When you run simulations of isopopulations and fold in realistic survey biases, you get empty cone patterns. Directions on the sky where you'd expect to find an ISO but don't find a parent star, not because the parent isn't there, but because it's too faint or lacks a radial velocity measurement, or is just outside the survey volume. Atlas might be sitting in one of those empty cones, and if it is, then the mystery isn't cosmological, it's observational. Now, I'm going to acknowledge something that's been buzzing in the public discourse: Mars flyby, Jupiter alignment, ecliptic plane crossing. These are real geometric facts. Atlas did pass relatively close to Mars. Its trajectory does intersect regions where planets orbit. But here's what orbital mechanics actually tells you. Any hyperbolic visitor entering the inner solar system has to cross the ecliptic plane somewhere. The planets are all roughly in that plane, so crossing near a planet isn't special, it's almost unavoidable. The probability calculation people throw around, what are the odds? Those calculations often forget to include the search space. If you ask, what are the odds this specific trajectory passes within X distance of Mars on this specific date, the number looks tiny. But if you ask, what are the odds any interstellar object we discover passes within some distance of some planet at some time, the number gets much larger. You're changing the question. Here's a visual I wish I could show you. Imagine a sky map with predicted iso-radiant density overlaid. Darker regions are where models say you're more likely to see an ISO arrive from. Lighter regions are less likely but not impossible. Atlas's radiant sits in a region that's not the darkest, not the lightest. It's in the middle of the distribution, and when you overlay survey coverage, you see why we might have found it. Not because it's aimed at us, but because we were looking in a direction where objects like it could be found. What about the alignment with the solar apex? The Sun is moving through the local standard of rest at about 240 kilometers per second in a direction toward the constellation Hercules. Atlas' inbound velocity vector has some component aligned with that motion. But again, so what? Disk stars and ejected objects from disk stars will have velocity distributions that reflect the overall galactic rotation and the Sun's motion. Some will be aligned, some will be counter-aligned, some will be perpendicular. Atlas being somewhat aligned is not evidence of targeting, it's evidence of coming from the disk. I want to be clear about something. The coincidences people notice, the close approach to Mars, the timing, the radiant direction, they're not meaningless. They're interesting, they make the story compelling. But interesting and compelling do not mean anomalous. The cure for coincidence anxiety is better statistics and more samples. When we have 10 interstellar visitors, we'll see how many pass near planets. When we have 100, we'll map the radiant distribution. Right now, with a sample size of 3, we're in anecdote territory, not statistics. What will additional astrometry tell us post-perihelion? A refined radiant. A better measurement of the inbound velocity vector. Those will tighten the constraints on where Atlas came from on the sky, and how fast it was moving before the sun grabbed it. If the radiant shifts significantly with better data, some of the alignment talk will evaporate. If it stays roughly where it is, we'll have a more precise target for future traceback attempts when better stellar catalogues come online. Speed isn't just about where, though. It's about how fast relative to the local standard of rest. And Atlas's speed is high. Not impossibly high, but high enough that people have started asking uncomfortable questions. Because in the galactic velocity field there are patterns. Young stars move slowly relative to the LSR. Old stars move quickly. The speed of an object encodes its dynamical age, the time it's spent being gravitationally kicked around. And if you take Atlas's speed seriously, if you calculate how long it would take to build up that velocity through natural processes, you get a number that's unsettling. Atlas might be older than you think. Part 7. The Forbidden Speed Window. 58 kilometers per second. That's Atlas's inbound velocity relative to the Sun. The orbital eccentricity is about 6.1, solidly hyperbolic. Not marginally unbound, like some long-period comets that creep in from the Oort cloud. Deeply hyperbolic, unmistakably interstellar. But here's the thing. 58 kilometers per second is fast compared to long-period comets, which typically enter the inner solar system at 10 to 30 kilometers per second. It's not, however, outside the predicted range for interstellar objects ejected from planetary systems. Some population models predict ISOs with velocities up to 70 or 80 kilometers per second. So Atlas is fast, but not impossibly fast. Unless you start thinking about age. Kinematic age dating is tricky, but it's been tried. Hopkins and Taylor-Seligman published age estimates based on Atlas's velocity distribution. Their numbers range from about 3 to 11 billion years, depending on the priors and assumptions. Another study pushes the lower bound to over 7.6 billion years. Those are not tyrannosaur ages. Those are ages that predate the formation of the solar system. The Sun is 4.6 billion years old. Earth is 4.5 billion years old. If Atlas is 7 billion years old, it was wandering the galaxy when our solar system was still a collapsing cloud of gas and dust. Let me explain the logic in plain terms. The local standard of rest is the average velocity of stars in the solar neighbourhood. It represents the bulk flow of the galactic disk. Young stars, stars that formed recently from well-mixed gas, move close to the LSR. They haven't had time to be gravitationally perturbed. Old stars, stars that have orbited the galaxy dozens or hundreds of times, have been kicked by passing stars, molecular clouds, spiral arm crossings. Each kick adds velocity. Over time, the star's motion becomes offset from the LSR. The offset, the peculiar velocity, is a clock. The bigger the offset, the older the object, statistically speaking. Atlas's motion shows a large offset from the LSR. That suggests age. But here's the nuance. The relationship between velocity dispersion and age isn't one-to-one. It's statistical. You can have a young object with a large peculiar velocity if it got a big kick early. You can have an old object with a small peculiar velocity if it got lucky and avoided major perturbations. So when someone says Atlas is 7 billion years old, they're giving you a probabilistic statement based on population averages, not a definitive measurement. But even with that caveat, the numbers skew old. Why does forbidden window language show up? Because people expect interstellar objects to have velocity distributions that mirror nearby stars, and nearby stars have a roughly Gaussian spread around the LSR. But that's not quite right. Real velocity distributions are not Gaussian, they're clumpy. Moving groups, stellar streams, associations, all of those create substructure in velocity space. If Atlas came from a moving group or a dissolved cluster, its velocity could reflect that group's bulk motion, not just its individual age. So the forbidden window idea, the notion that Atlas's speed is too high to fit natural explanations, it collapses when you account for galactic substructure. What natural processes can accelerate or decelerate an object over billions of years? Stellar flybys. Every time Atlas passed within a few parsecs of a star, it felt a gravitational tug. Small tug, but over billions of years, Small tugs add up. Molecular clouds. Dense regions of gas in the galaxy can exert drag or gravitational slingshots depending on geometry. Galactic tides. The Milky Way's gravitational potential isn't uniform. Orbits in that potential can gain or lose energy over time. Spiral arm crossings. The density waves that create spiral arms can perturb objects passing through them. All of these are natural, well-understood processes. Given enough time, they can push an object's velocity to tens of kilometers per second relative to the LSR. But now let me float some speculative ideas, and I need to label these as imagination. Fuel, not claims. Could interstellar medium magnetic drag slow down a charged object over billions of years? In principle, yes, but the effect is tiny unless the object is moving through a very dense, very magnetized region. Could interaction with a non-Newtonian gravitational medium, some exotic dark matter or modified gravity regime, alter an object's speed without stellar encounters? That's fringe physics, not supported by current observations, but it's an idea that gets tossed around in certain circles. Could artificial deceleration, a propulsion system that's been intermittently firing over billions of years to adjust the trajectory, explain a seemingly tuned velocity? Again, pure speculation, no evidence, but it's out there in the discourse. How would you test exotic braking ideas? Spin state evolution. If Atlas has been subjected to external torques beyond normal outgassing, its rotation might show anomalies. Coma jet torques. If jets are firing asymmetrically in a way that damps orbital changes rather than amplifying them, that's measurable. Pre-perihelion versus post-perihelion velocity shifts. If Atlas's speed relative to the Sun changes by an amount inconsistent with gravitational interactions and cometary outgassing, that's a red flag. None of those anomalies have been detected. So for now, exotic braking is a solution in search of a problem. Here's the bridge to the next piece. High speed plus old age equals information loss. If Atlas has been wandering for billions of years, the number of stars it's passed, the number of gravitational interactions it's experienced, is astronomical. Each interaction adds noise to the orbital history. By the time 10 million years of backward integration is complete, you're not tracking the real trajectory anymore. You're tracking one possible trajectory in an exponentially growing cloud of possibilities. The timeline doesn't just fade, it vanishes into chaos. Part 8. The timeline that vanishes. Imagine you're trying to reconstruct the path of a single pebble in a riverbed after 10 million years of water flow. The pebble is still there, you can hold it in your hand. But the specific route it took to get from upstream to your hand, that's gone. Washed away by trillions of tiny turbulent eddies, each one nudging the pebble in a slightly different direction. The physics is reversible in principle. Newton's laws work forward and backward, but the information needed to reverse the trajectory, the position and velocity of every water molecule at every instant, that information has dissipated into entropy. Atlas is the pebble, the Milky Way is the river, and 10 million years is a very long time. Perikuto's team stopped their traceback at 10 million years because beyond that point, meaningful ancestry search dies. The reason is twofold. First, chaos. Stellar orbits and interstellar object orbits are chaotic systems. Small uncertainties in initial conditions grow exponentially. By 10 million years, the phase space of possible trajectories has exploded into a cloud so large that you can't meaningfully distinguish one path from another. You're not computing history anymore, you're computing noise. Second, catalogue limits. Gaia has radial velocities for only a fraction of stars, mostly bright ones, within a few hundred parsecs. Beyond about 500 parsecs, the RV completeness drops off a cliff. So even if Atlas came from a star 2 kiloparsecs away, we wouldn't have the data to test it. 10 million years is where observational limits and dynamical chaos meet, and both tell you to stop. Cosmic amnesia is not a failure of physics. It's a feature of information theory. The universe doesn't keep a ledger of every trajectory. Information is constantly being thermalized, mixed, lost to entropy. An object's past exists in the physical sense. Causality is real, but the retrievability of that past is not guaranteed. After enough time, after enough interactions, the causal chain is still there in principle, but untraceable in practice. Atlas has a past. It came from somewhere. But the universe's bookkeeping system has shredded the receipt. Why does this matter beyond 3i? Because we're about to enter the era of frequent interstellar object discoveries. The Vera-Rubin Observatory, formerly LSST, is coming online. It will survey the entire southern sky every few nights, going deep, finding faint objects. Estimates suggest Rubin could find dozens to hundreds of interstellar visitors per year once it's fully operational. Most of those will be old, like 3I. Most will have untraceable origins, but some, the lucky ones, will be freshly ejected. Objects that left their parent star a few 100,000 years ago, maybe 1,000,000 years tops. For those objects, the amnesia hasn't set in yet. The orbital history is still retrievable. Those are the ones we can trace. What would it take to trace Atlas if better data came along? Better stellar radial velocities for fainter stars? Gaia's future releases will push the magnitude limit deeper, but there are fundamental limits to how faint you can measure RVs from the ground or even from space. Gaia successors, hypothetical missions that could map stars to 10th magnitude or fainter with full 6-dimensional data. Local interstellar medium mapping. If we knew the density and velocity structure of gas and dust along Atlas' past trajectory, we could model drag and perturbations more accurately. But all of that is future tense. Right now, Atlas's timeline vanishes into the fog. There's a philosophical beat here that's worth pausing on. Physical causes exist. Atlas was ejected from a planetary system. That ejection had a cause. The star that ejected it exists or existed. The gravitational interactions that shaped Atlas's path over billions of years, those happened. None of that is in question. But causal retrievability, the ability to reconstruct the chain of causes from present observations that can fail, not because the causes didn't happen, but because the information has been scrambled beyond recovery, is like asking what the weather was on a specific day 3 billion years ago. The weather happened. It had causes. But the information is gone, mixed into the thermal noise of the atmosphere and oceans and crust. Atlas's origin is gone in the same way, not erased, but irretrievable. There's a tie back to chemistry here. If we can't track where Atlas came from dynamically, we can still read what it's made of. The CO2 dominance, the polarization signature, the dust properties, those are environmental clues. They don't tell you the address of the parent star, but they tell you what kind of neighborhood it lived in. Cold, carbon-rich, possibly old, that's not nothing. In the absence of orbital genealogy, chemistry becomes the breadcrumb trail. Let me push the speculation one step further, clearly labelled. If Atlas is truly ancient, if it's been wandering for 7 or 10 billion years, it predates major events in galactic history. The last major merger, the Gaia-Enceladus collision, happened about 10 billion years ago. That event brought a dwarf galaxy into the Milky Way, stirring the disk, triggering star formation, altering the chemical makeup of the galaxy. If Atlas predates that, it formed in a pre-merger galactic environment. Its chemistry could reflect a Milky Way that no longer exists. That's a long shot, but it's tantalizing. I mentioned earlier that some studies, like Go et al. Gases, report many close stellar passages in their tracebacks. Their numbers don't match Perez-Couteau's. Why? Different initial conditions, different orbital uncertainties, different stellar samples, different integration methods. When you reconcile the methodologies, the discrepancies make sense. But here's the consensus. No matter which study you read, no matter whose numbers you trust, the bottom line is the same. No parent star identified, plenty of close passages, but none close enough or slow enough to matter. The timeline is scrambled for everyone, so time has scrambled the past. Orbital traceback is a dead end, but Atlas is still here, it's still active, it's wrapped in a coma of gas and dust. We have the most advanced telescopes in human history pointed at it. Hubble, Webb, ground-based instruments, and yet there's a curious silence. A lack of certain kinds of data you'd expect to have by now. Some of that is physics, some of it is logistics, but in the gaps, speculation grows. Part 9. The Silence of the Sensors. Hubble looked at 3I. It set an upper limit on the nucleus size of about 5.6 kilometers. That's not a direct detection. It's a limit based on how much light Hubble can see that's not coming from the coma. The nucleus itself is buried in the glow of gas and dust, so you can't just image it directly. You model the coma, subtract it, and see what's left. What's left for Atlas is consistent with a nucleus somewhere between about 0.32 and 5.6 kilometers, depending on assumptions about albedo and activity. Could be a few hundred meters, could be a few kilometers. We don't know yet. What we don't have, and this needs to be said plainly, is radar data. No radar echoes from 3i. Why not? Because radar astronomy for small bodies requires the target to be relatively close and the radar cross-section to be large enough to detect. Atlas has been too far away for effective radar ranging with current systems. Arecibo, which could have done it, collapsed in 2020. Goldstone and the Green Bank telescope have tried for some targets, but Atlas's distance and geometry make it impractical, so no radar, no conspiracy, just physics and logistics. Thermal infrared data is more subtle. Webb's near-infrared spectrograph gave us gas, ice and dust spectral features, but extracting a clean thermal inertia measurement of the solid nucleus requires separating the nucleus's thermal emission from the coma's scattered sunlight and dust emission. That's hard when the coma is active, so interpretations of whether the nucleus has a thick crust, a porous structure, or something exotic, those are premature. We don't have the data to make those calls definitively yet. Light curve irregularities have been reported in some ground-based photometry, brightness variations over time, but here's the problem. The nucleus is veiled by the coma. You're not seeing the bare rock. You're seeing rock plus gas plus dust, all varying together. Disentangling rotation period, shape and activity level from pre-perihelion photometry is extremely difficult. Some teams are working on it, but the results are preliminary. So claims about unusual rotation states or non-principal axis tumbling, those are speculative at this stage. Let me reiterate something important. No non-gravitational acceleration has been detected in Atlas's orbit, despite visible activity. That's a clean, boring answer. Boring can still be weird when you think about the coma physics. Active comets usually show NG acceleration. Atlas doesn't, at least not yet. That's unusual, but as I discussed earlier, it's explainable. Symmetric venting, CO2 instead of water, spin geometry, all plausible. The point is, the absence of NG acceleration is not evidence of artificial stabilization or exotic physics. It's just an interesting data point that might resolve as we get more astrometry. Now let's talk about media versus papers. Headlines about Manhattan-sized objects, wow images from the Mars flyby, dramatic visualizations, those exist. They're illustrative. They help the public engage with the story. But when you anchor on NASA, HST and JWST outputs, the actual science releases, the tone is much more measured. Nucleus size is uncertain. Coma is CO2 rich. Polarization is unusual. That's what the papers say. The gap between headlines and data is where confusion breeds. The Mars pass happened on September 29th to 30th, 2025. Atlas came within about 29 to 30 million kilometers, roughly 18 million miles. That's not a close flyby in the sense of skimming the atmosphere. It's a great geometry for Mars orbiting assets. ESA's Mars Express, NASA's MAVEN, rovers with cameras, all had a chance to observe from a different vantage point than Earth. Multiple baselines mean better triangulation of the coma structure, better constraints on outgassing direction, possibly even a detection of faint features invisible from Earth, so the Mars pass was scientifically valuable, even if it wasn't cinematic. Here's where I need to address something floating around online. Claims about withheld spectra, suppressed data. The idea that teams have data they're not releasing because it's too anomalous. Let me be very clear. Large telescope programs have processing pipelines. Data goes from raw images to calibrated spectra to published results through a workflow that takes months. Peer review takes time. Proprietary periods exist to give the teams who propose the observations time to analyze before public release. This is standard. Absence of a plot on day one is not evidence of suppression. It's evidence of how science works. If you want real-time data releases, advocate for open access policies and pipeline automation. But don't confuse logistics with conspiracy. What should we watch for in the next data releases? Perihelion gas ratios. Does CO2 stay dominant or does water take over? Post-perihelion nucleus size estimates. As the coma evolves, coma subtraction might get cleaner, allowing a tighter constraint on the solid body. Non-gravitational acceleration terms. If A1 and A2 appear in the orbit fits after perihelion, that tells us water jets are kicking in. High signal-to-noise spectroscopy. If someone gets a really clean spectrum, we might see trace species, deuterium to hydrogen, carbon isotopes, sulfur compounds. Those would be gold for formation environment inferences. The sensors are not silent because something is hiding. They're silent because the measurements are hard and the object is far and the data pipeline is slow. That's not satisfying, I know. But it's honest. And honesty is what separates science from storytelling. Though, speaking of storytelling, there's an elephant in the room that we've been dancing around. The culture war in astronomy. The debate that's not really about data. It's about interpretation, media, and what it means to call something artificial. Part 10. The Academic Cold War. Let me set the landscape as neutrally as I can. The mainstream astronomical community, the teams publishing in refereed journals, the observers running the telescopes, they call Atlas a natural interstellar comet with unusual traits. CO too rich, high peculiar velocity, extreme polarization, untraceable origin, all interesting, all within the bounds of natural astrophysics. But there's a minority perspective, most prominently championed by Avi Loeb and collaborators at Harvard, that publicizes techno-artifact hypotheses, not as definitive claims, at least not officially, but as possibilities worth investigating, and that difference in framing has created a rift. Loeb's talking points, drawn from blog posts and essays, include things like ecliptic and planetary alignments, optimized close approaches, extreme polarization as a potential signal, even claims about nickel without iron in hypothetical material composition, though that last one is not peer review consensus. The argument goes something like this. If you calculate the odds of Atlas's trajectory coincidentally passing near Mars and Earth at geometries convenient for observation, the numbers look small. If you add in the unusual chemistry and polarization, the prior probability of all those things being natural drops further. At some point, Loeb argues, you have to consider the alternative, that Atlas is not a comet, that it's a probe, a relic, something made. The community pushback has been swift and pointed. Senior astronomers like Jason Wright, who runs the Penn State Extraterrestrial Intelligence Center, have critiqued the methodology. Selection effects, they say, are not being properly accounted for. Post hoc probability framing, calculating the odds after you've seen the outcome, is a classic statistical fallacy. Media incentives, the fact that artificial intelligence claims generate headlines and funding attention, create perverse incentives to hype speculation over data. Wright and others have written extensively about why low probability does not mean impossible, and why extraordinary claims require extraordinary evidence, not just extraordinary press releases. Why do these terms matter? Because words shape funding. If Atlas is called an interstellar visitor, it gets studied by planetary science programs. If it's called a potential technological relic, it gets studied by SETI programs, or it gets elevated to national security attention, or it attracts private funding from donors interested in existential questions. Mission proposals change. Agency risk posture changes. The James Webb Telescope didn't point at Atlas because someone thought it might be a spaceship. It pointed at Atlas because it's an interstellar comet, and JWST can characterize volatiles. But if the narrative shifts, future pointings might be justified differently, and that feedback loop between narrative and resource allocation is what makes this more than an academic debate. There's a historical case study here. Oumuamua. When One Eye passed through in 2017, the lack of a visible coma combined with non-gravitational acceleration sparked speculation. Loeb co-authored a paper exploring light sail scenarios, hypothetical thin reflective structures pushed by radiation pressure. The paper was technically sound as an exploration of parameter space. But the media coverage and subsequent blog posts elevated the idea to something more than a what-if. Public perception shifted. By the time 2I Borisov arrived and behaved like a normal comet, the damage was done. Interstellar objects were now, in the public mind, potentially artificial until proven natural. Atlas inherited that baggage. What's changed between Oumuamua and 3I? Better early coverage. JWST exists now. Webb can characterize chemistry in ways that weren't possible in 2017. Ground-based polarimetry has improved. Astrometry is tighter, so the data stream for Atlas is richer, faster, and more detailed. That should make the natural versus artificial question easier to resolve. But it also means more data points for both sides to selectively emphasize. Here's my editorial stance for this script. We include speculation as speculation. We separate blog claims from refereed results. We encourage tests that could falsify both natural and artificial hypotheses. Because the worst outcome is not that we investigate a weird idea and find it's wrong. The worst outcome is that we don't investigate and miss something real. Science is not about shutting down ideas. It's about testing them. What are the practical tests? Repeatable polarimetry across a range of phase angles. If the negative branch is due to exotic grain properties, it should be reproducible and modelable. If it's a fluke or an artifact of early geometry, it'll change. Volatile ratio evolution through perihelion. Natural comets have predictable behavior as they warm up. If Atlas deviates from that, it's interesting. Post-perihelion non-gravitational fits. If A1 and A2 terms appear and match cometary outgassing, natural explanation wins. If they don't appear despite strong activity, or if they appear with weird geometries, that's a puzzle. High signal-to-noise spectroscopy for odd metals. If someone claims Atlas has nickel without iron, show me the spectrum. Refereed, calibrated, with error bars. Until then, it's a claim, not data. Media literacy matters here. When someone says the probability of Atlas's trajectory is 1 in a million, ask what the search space is. 1 in a million sounds impressive until you realize you're checking a million possibilities. When someone says a feature is unprecedented, ask unprecedented compared to what sample size. 3 interstellar objects is not a statistically robust sample. When someone invokes Occam's razor, remember that Occam doesn't say the simplest explanation is always right. It says don't multiply entities beyond necessity. Natural explanations for Atlas exist. They're not simple, but they're sufficient. Artificial explanations require more assumptions, alien civilizations, interstellar travel, deliberate targeting. Those assumptions need more justification than it looks weird. Here's the constructive note. Even wild ideas motivate observations. If someone says Atlas might be artificial, and that claim gets JWST time or prompts a new polarimetry campaign, and the data come back showing it's natural but revealing new comet physics in the process, then the wild idea paid off. The cure for hot takes is not silence. It's more data, better data, data that constrains the possibilities until only one explanation is left standing. So if Atlas is natural, what natural models survive? What stories can we tell that fit the chemistry, the polarization, the kinematics, the untraceable origin? That's where we go next. Because natural doesn't mean boring. Natural can be ancient, exotic, and deeply strange. And some of the natural models for Atlas are, in their own way, as mind-bending as anything artificial. Part 11. The Phantom Models. Let me walk you through some scenarios that could produce an object like Atlas without invoking engineering. These are working hypotheses, not definitive answers. Each one fits part of the data, none fits everything perfectly, but that's okay. Science progresses by testing models against observations, not by waiting for a perfect theory to descend from the sky. Scenario 1. Primordial debris from galaxy interactions. The Milky Way has had a violent history. It's eaten smaller galaxies. Gaia Enceladus, the Sagittarius dwarf, others we're still mapping. When a dwarf galaxy merges with the Milky Way, it doesn't just dump stars, it dumps everything. Gas, dust, planetesimals, small bodies. Some of that debris gets stirred into the Milky Way's halo, some settles into the disk. If Atlas is a fragment from one of those ancient mergers, it could have been wandering for billions of years, ejected from its parent system long before the Milky Way had its current structure. That would explain the old kinematic age. It would explain why we can't trace it to a nearby star. And if the dwarf galaxy had different metallicity or different volatile chemistry than the Milky Way, that might explain the CO2 dominance. Feasible? Yes. Provable? Not with current data. Scenario 2. Rogue planet crust shattering. Imagine a super-Earth or mini-Neptune ejected from its planetary system. It wanders into stellar space for billions of years. At some point it passes close to a star, not close enough to be captured, but close enough for tidal forces to stress the crust. The crust fractures. Shards break off. Some of those shards are rich in CO2 if the mantle chemistry favoured carbon dioxide ices. Those shards become interstellar comets. Atlas could be one such shard. That would explain a potentially large, dense nucleus, consistent with Hubble's upper limit of 5.6 kilometres. It would explain unusual chemistry, but it's speculative. We have no direct evidence of rogue planets shattering near stars. It's a plausible mechanism, not a confirmed one. Scenario 3. Post-main sequence ejections. When a star leaves the main sequence, when it becomes a red giant or sheds mass. As a white dwarf, the planetary system gets rearranged. Orbits destabilize. Some planets fall in, some get ejected. Volatiles that were locked in the outer system can get redistributed. If Atlas was ejected during a post-main sequence phase, it might have acquired unusual volatile ratios through thermal processing during the red giant phase. CO2 could be enhanced if carbon and oxygen were abundant in the star's outer layers and got mixed into the planetary debris. This scenario explains old age, explains untraceable origin if the parent star is now a faint white dwarf, and explains weird chemistry. But again, it's a could, not a did. Scenario 4. Molecular cloud condensation dark comets. This is a niche theory, not widely accepted but worth mentioning. The idea is that small bodies, not full planets, can grow directly in dense molecular cloud filaments without forming a star or planetary system first. These would be fragments of prestellar cores, tiny ice balls that condense in the coldest, densest regions and then get dispersed when the cloud is disrupted by nearby star formation or supernova shocks. If Atlas formed this way, it would have chemistry reflecting the molecular cloud environment, which can be CO2 rich depending on carbon and oxygen abundances. But this mechanism is model-dependent and controversial. Most astronomers think small bodies need a protoplanetary disk to form, not just a cloud. So this is speculative even by the standards of phantom models. Scenario 5, captured then released in the Milky Way halo. What if Atlas isn't from the disk at all? What if it's an intergalactic traveller that was captured by the Milky Way's halo potential billions of years ago, orbited in the halo for ages, and only recently dropped into the disk due to some perturbation? That would explain why it's kinematically consistent with the thin disk now but has no local parent. It would explain old age. It's hard to prove because we can't trace halo orbits over year timescales, but it's conceptually feasible. The chemistry would depend on where it originally formed, possibly in a satellite galaxy or even in intergalactic space if such formation is possible. How do these models stack up against Atlas's data? CO2 to water ratio of 7.6. Models 2 and 3 can potentially explain that through mantle composition or post-main sequence processing. Model 1 depends on the dwarf galaxy's chemistry. Model 4 depends on molecular cloud chemistry. Model 5 is a wildcard, extreme negative polarization branch. All models allow for unusual dust if the formation environment or processing history differed from solar system norms. No detected non-gravitational acceleration despite activity. All models are consistent with that if the nucleus is massive enough or venting symmetric enough. Thin disk kinematics. Models 1 and 5 have the hardest time with this unless you invoke specific capture or migration scenarios. Models 2, 3, and 4 naturally put Atlas in the disk, so we can rank plausibility loosely. Models 2 and 3, rogue planet shards and post-main sequence ejections, fit the most data with the fewest exotic assumptions. Model 1, primordial merger debris, fits the age and kinematics but requires specific chemistry. Model 4, molecular cloud condensates, is the most speculative. Model 5, halo capture, is conceptually interesting but hard to test. What future observables could stress test these models? Dust size distribution from post-perihelion photometry. If we can measure how the brightness falls off with distance, we can infer grain size, which constrains coagulation history. Volatile isotope ratios, deuterium to hydrogen, carbon-13 to carbon-12, nitrogen-15 to nitrogen-14. Those would fingerprint the formation environment's temperature and chemistry, deep imaging for fragmentation. If Atlas starts shedding pieces as it warms up, that tells you about structural integrity, which relates to formation history. All of those are hard measurements, but not impossible. Plain takeaway. More than one natural path can land you at CO, too rich, old, and untraceable. We don't need to invoke engineering to explain 3I. We just need to accept that interstellar objects can come from formation environments and dynamical histories we don't fully understand yet. And that's exciting, because it means every interstellar visitor is a messenger from a corner of the galaxy we can't reach any other way. But let me take this one step further. What if Atlas isn't just old? What if it's ancient? What if it predates not just the solar system, but the Milky Way's current structure? What if Atlas is a cosmological outsider, a relic from the early universe of star and planet formation? Part 12. The Cosmological Outsider. 3 to 11 billion years. That's the age range inferred from Atlas's kinematics. The lower end of that range makes it older than the Sun. The upper end makes it one of the oldest solid objects we've ever encountered. To put that in perspective, the universe is about 13.8 billion years old. The Milky Way's disk began forming around 10 to 12 billion years ago. If Atlas is at the older end of those estimates, it formed when the galaxy was young, when metallicity was lower, when the first generations of planetary systems were just beginning to coalesce around population 2 stars. Now, I need to be very clear about something. These age estimates are statistical, not direct measurements. We're inferring age from velocity dispersion, from how much Atlas's motion has been scattered relative to the local standard of rest. That gives you a probabilistic age based on population models. It's not like carbon dating, it's not a number you can write down with 2 decimal places and call definitive. But even with that uncertainty, even with the error bars, the numbers push old. Older than feels comfortable. Older than the solar system is not speculation, it's plausible. So let me float a speculative question, clearly labelled as thought experiment territory. Could Atlas be among the earliest solid bodies in the galaxy? Could it be a first-generation planetesimal from a low metallicity system? Early stars, the ones that formed in the first billion years of the galaxy's history, had less iron, less silicon, less of the heavy elements we associate with rocky planets. But they still had oxygen and carbon from Big Bang nucleosynthesis and the first supernovae. A planetary system around a metal-poor star might have different chemistry. More volatiles relative to rock, more carbon and oxygen compounds, more CO2 relative to silicates. That could explain Atlas's chemistry if it's truly ancient. The problem is we don't have the data to test that. Isotope ratios would be the smoking gun. Deuterium to hydrogen, D to H, is set during Big Bang nucleosynthesis, but gets modified by stellar processing and local chemistry. Carbon-13 to carbon-12, oxygen-18 to oxygen-16. Those trace temperature and chemical environment during formation. If Atlas has isotope ratios that are off the solar system curve, that would tell us it formed somewhere chemically distinct. But we don't have those measurements yet. JWST's spectroscopy is good, but it's not that good. You need very high spectral resolution and signal-to-noise to pull out isotope lines. Maybe post-perihelion, when the coma brightens, someone will try. But for now, it's a wish list item. Here's a brief primer on why isotopes matter, kept accessible. Big Bang nucleosynthesis produced hydrogen, helium, a bit of lithium, and trace deuterium. Everything heavier came from stars. When stars fuse hydrogen into helium, helium into carbon, carbon into oxygen, they create specific isotope ratios depending on temperature and pressure. When supernovae explode, they spew those isotopes into the interstellar medium. New stars form from that enriched gas. Planets form from the leftover disk. The isotope ratios in planets reflect the composition of the gas cloud they formed from. If you measure isotopes in a comet, you're reading the chemical signature of its birth environment. Solar system comets have solar isotope ratios, broadly speaking, because they formed from the same cloud as the Sun. If Atlas has non-solar isotope ratios, it formed elsewhere. And if those ratios are consistent with low metallicity early galaxy conditions, that's a timestamp. Let me tie this to galactic history. The Milky Way's disk has structure. There's a thin disk, where we live, full of relatively young, metal-rich stars. There's a thick disk, older, more metal-poor, with stars that have higher velocity dispersions. The halo is even older, even more metal-poor, full of stars from the galaxy's earliest days and from accreted dwarf galaxies. Atlas's kinematics say thin disk, but with a large peculiar velocity that pushes it toward the boundary between thin and thick. That's not uncommon for old objects. Over billions of years, gravitational stirring can blur the lines between populations. So kinematically, Atlas could be a thick disk object that's been scattered into thin disk-like orbits. Or it could be an ancient thin disk object that's accumulated a lot of velocity kicks. Kinematics alone don't uniquely tell you. But if you add chemistry, if you add the CO2 dominance and the unusual dust, you start to narrow the possibilities. Thick disk and halo stars tend to be metal-poor. If Atlas formed in a metal-poor environment, that might favour CO2 over silicate-rich dust, because there's less rock to work with. That's speculative, but it's a thread worth pulling. If Atlas is verified as older than the solar system, what does that do to our narratives? It stretches them. We're used to thinking of comets as solar system natives, leftovers from our sun's formation. Interstellar objects are foreign, yes, but we still imagine them as contemporaries, formed around stars of similar age in the same general epoch of galactic history. An ancient interstellar object challenges that. It's not a peer, It's an elder. It was wandering the galaxy when the molecular cloud that would become the solar system hadn't even started collapsing. It witnessed star formations we'll never see. It carries chemistry from an era of the galaxy we can only infer from old stellar spectra. That's humbling. But let me add a caution. Do not overclaim pregalactic. That's beyond evidence. We have no data suggesting Atlas formed before the Milky Way existed. The universe had galaxies by the time Atlas could have formed, so it's a galactic object, not a pregalactic relic. The thought experiment is whether it's older than most galactic structures we interact with, not whether it predates galaxies. Keep it grounded. Here's a visual I wish I could show you. A timeline. Start at the Big Bang, 13.8 billion years ago. Mark the formation of the first stars, a few 100 million years after the Big Bang. Mark the formation of the Milky Way's halo, about 12 billion years ago. Mark the thick disk, 10 to 12 billion years. Mark the thin disk, 8 to 10 billion years. Mark the Sun, 4.6 billion years. Now place Atlas on that timeline with error bars. The lower end sits around 7 billion years. The upper end pushes past 10 billion years. Atlas spans the gap between the Sun's formation and the galaxy's youth. It's a time capsule with a scratched label. Why do audiences love this framing? Because it recontextualizes the object. It's not just a comet. It's a message in a bottle from deep time. It's physical evidence that the galaxy is old and full of histories we'll never fully know. It connects the abstract notion of cosmic time to a tangible, trackable object you can point a telescope at. And that connection, that sense of reaching across billions of years to touch something ancient that's powerful. But here's where the narrative takes a turn. If Atlas isn't a transmitter, if it's not broadcasting, if it's not signaling, could it still be a carrier? Could it encode information not in radio waves or laser pulses, but in its structure, its chemistry, its polarization? That's the premise of the next idea, one that lives firmly in speculative territory, but that's interesting enough to explore. Not because it's likely, but because it's testable. Part 13. The Hidden Communications Theory. Let me set expectations right at the top. This entire section is speculative. There is no peer-reviewed evidence that Atlas is artificial. There is no data suggesting it's a communications device. What follows is a thought experiment, a what-if scenario that explores how one might encode information in a passive object and what it would take to detect such encoding. This is science fiction adjacent territory, but it's grounded in real physics and real observational techniques. Think of it as a puzzle, not a claim. The idea of non-signal intelligence is not new in SETI circles. Traditional SETI looks for electromagnetic signals, radio or optical beacons, deliberate transmissions. But there's a school of thought that considers passive information encoding, objects that don't broadcast but that carry information in their structure, a probe that encodes its origin or purpose in the way it scatters light, or the way its surface reflects, or the geometry of its orbit. You wouldn't need power, you wouldn't need electronics. You just need careful design and a recipient capable of noticing. How would you hide information in polarization? Polarization is a function of grain size, shape, porosity, composition, and scattering angle. If you could control the microstructure of dust grains, you could in principle design a polarization phase curve with specific features, a dip at a certain angle, an inversion at another angle, modulation of depth or width with wavelength. To a natural observer, it would look like dust. To an informed observer who knows to look for patterns, it might encode metadata. What kind of metadata? Coordinates, a timestamp, a signature. The challenge is distinguishing designed modulation from natural variation. Atlas's polarization curve has a deep, narrow negative branch at about 7 degrees phase angle, inverting around 17 degrees. Is that design or dust? Almost certainly dust. Natural scattering explains it without invoking encoding. But as a thought experiment, if you wanted to encode information in that curve, you'd need high-cadence polarimetry across many wavelengths and phase angles. You'd look for deviations from smooth models, sharp features that don't fit natural grain distributions, periodic modulations that correlate with spin or orbital phase. None of that has been seen in 3I. The polarization is unusual, but it's consistently unusual in ways that match exotic but natural dust models. What about anti-tails and dust jets as barcodes? Comets sometimes produce anti-tails, faint extensions that point toward the sun rather than away. They're caused by large dust grains on specific orbital geometries, If you could control the timing and direction of dust release, you could, in principle, create patterns. Intensity versus angle, brightness versus time, a sequence of pulses. To detect that, you'd need time-resolved imaging with high spatial resolution. You'd need to watch the coma evolve over hours or days and look for structure that doesn't fit hydrodynamic models. Again, none of that has been reported for 3I. The coma is asymmetric, sunward enhanced, but that's what you'd expect from solar heating. No barcode, no sequence. Here's the SETI context. Silent probes, sometimes called Bracewell probes, are a discussed concept. The idea is that an advanced civilization might send out probes that don't transmit until they detect intelligent life. They lurk, they observe, they wait. If Atlas was such a probe, it would be passive now, watching, recording, but not signaling. How would you test that? You'd look for responses. You'd broadcast at it and see if anything broadcasts back. You'd watch for trajectory changes that don't fit natural forces. You'd monitor for emissions, gamma rays, neutrinos, anything that doesn't come from cometary activity. None of that has been detected. Atlas is silent. What actual data could check for encoding? Multiband polarimetry, observing at optical, near IR, and mid-IR wavelengths to see if polarization features correlate across the spectrum in non-natural ways. High time resolution photometry, looking for periodic brightness variations that encode binary sequences. Dust spectroscopy, checking for absorption or emission lines from materials that don't belong in comets, metals that aren't oxidized, organics with unnatural complexity. Radio monitoring just in case. All of those are technically feasible. Some have been tried. Nothing anomalous has turned up. Where does the encoding idea likely fail? Occam's razor. Natural scattering explains Atlas's polarization. Natural cometary outgassing explains the coma. Natural orbital dynamics explain the trajectory. You don't need to invoke design. And the burden of proof is on the extraordinary claim. If you claim encoding, you need to show structure that can't be explained naturally. Atlas doesn't show that. The polarization is weird, but weirdness is not evidence of intent. The universe is full of weird natural phenomena. So why include this section at all? Because extraordinary claims motivate extraordinary measurements. If someone says Atlas might encode information, and that prompts a new polarimetry campaign or a radio monitoring program, and the data come back negative but in the process reveal new dust physics or coma dynamics, then the claim was useful even if wrong. Science progresses not just by confirming hypotheses but by ruling them out. And ruling out encoding definitively requires taking the idea seriously enough to test it. Media caution. We will not conflate blog speculation with refereed science. On-screen citations will distinguish between peer-reviewed papers and opinion pieces. When we say someone claims encoding, we'll name the source and note whether it's a published result or a blog post. Transparency is how you maintain trust. The hidden communications theory is fun to think about. It's a thought experiment that respects the constraints of physics while pushing the boundaries of what's plausible. But at the end of the day, it's not where the evidence points. Atlas looks like a natural object with unusual properties. And unusual properties, as unsatisfying as it is to accept, are what you expect when you sample the diversity of planetary systems across the galaxy. Every system is different. Every interstellar visitor will surprise us. That's not a sign of artificiality. It's a sign of how little we know. But whether Atlas is natural or artificial, whether it's ancient or merely old, whether it's a comet or a shard or a relic, it bends our thinking about cause and origin. It forces us to confront the limits of what we can know and the difference between a thing existing and us being able to trace where it came from. That's where the philosophy lives. Part 14. The Philosophical Singularity. Let me repose the central riddle in the plainest terms I can. 3I Atlas is a real, physical object. It has mass, it has a trajectory, it has chemistry, it exists. But within our current data horizon, it has no retrievable past. We cannot trace it to a parent star. We cannot link it to a stellar encounter. We cannot reconstruct the chain of gravitational interactions that brought it here. The object is real. The history is gone. Not because the history didn't happen, but because the universe's bookkeeping has scrambled the ledger beyond recovery. This is not a paradox in the strict sense. Physics permits a cause. Atlas was ejected from a planetary system. That ejection had a cause. The star that ejected it exists, or existed, somewhere in the galaxy. The orbit that brought Atlas into our neighbourhood was shaped by millions of gravitational interactions over billions of years. All of that happened. Causality is not violated, but causal retrievability, the ability to reconstruct the chain from present observations, that can fail. Not because nature is hiding something, but because information dissipates. Entropy wins. Chaos wins. The universe does not owe us a history. Let me try an analogy. Imagine you find a bottle on a beach. The bottle is real. It's glass. It has barnacles. It has water inside. But there's no message, no label, no markings. You want to know where it came from. So you check ocean currents, you model the drift, you run simulations backward, but the ocean has been mixing for decades. Currents shift, storms happen, eddies form and dissolve. By the time you try to rewind the trajectory, the phase space of possible starting points has exploded. The bottle came from somewhere, but that somewhere is now anywhere along 1,000 kilometers of coastline. The bottle is real. The origin is unknowable. Atlas is the bottle. The Milky Way is the ocean. 10 million years is a very long drift. Now, I'm going to mention some physics concepts very lightly, as illustrative metaphors, not as literal claims about 3i. Retrocausality, the idea that effects can precede causes in certain quantum or relativistic frameworks. Closed time-like curves, solutions to general relativity where you could, in principle, loop back in time, atemporal reference frames, the notion that time is not fundamental but emergent from entropy. None of these apply to 3i. Atlas is a classical object moving through classical spacetime, but they're useful metaphors for thinking about how causality can exist even when causal chains are untraceable. The physics allows it, the information doesn't. Here's a cultural memory angle, the wandering stone archetype. Myths from dozens of cultures talk about stones that fall from the sky, stones that come from the void, stones that carry no history. Some myths treat them as messages from gods, others treat them as omens. Modern science treats them as meteorites or comets, objects with natural origins that we can trace. But Atlas breaks that pattern. It's a wandering stone we can't trace, and that resurrects the archetype. Not because we're abandoning science, but because we're confronting a limit that myth has always known existed. Some travellers have no map. Science philosophy has a principle here. Absence of evidence is not evidence of absence. We haven't found Atlas's parent star. That's absence of evidence. It doesn't mean the parent doesn't exist. But here's the flip side. When your catalogues are incomplete, when your search radius is limited, when your traceback methods have a 10 million year ceiling, absence of evidence starts to look like a hard epistemic wall. You're not ignorant, you're limited. The distinction matters. Ignorance is curable with more effort. Limitation requires new tools. What does Atlas expose about our current tooling? Gaia is spectacular. It's mapped over 1 billion stars with unprecedented precision, but it has limits. Radial velocities only for the bright ones, parallaxes only for the nearby ones, no coverage of the faint stars beyond a few hundred parsecs. If Atlas's parent is a red dwarf 500 parsecs away with no measured radial velocity, we'd never find it even if we looked forever. Interstellar medium mapping is even sparser. We don't have detailed density and velocity maps of gas and dust along arbitrary sightlines, so we can't model drag or perturbations from ISM interactions. Those are solvable problems, but they require next-generation surveys and missions that don't exist yet. Here's the invitation. Outline concrete upgrades that would shrink the ignorance cone for the next interstellar object. Gaia's successor missions with deeper magnitude limits and better RV coverage. All-sky surveys that track proper motions for stars to 15th magnitude or fainter. Interstellar medium tomography, using background quasars and pulsars to map gas density in 3 dimensions. Better galactic potential models that account for dark matter substructure and time-dependent features like spiral arms. More ESO detections to build population statistics so we know what's normal and what's not. All of that is technically feasible. It's a matter of funding and time. Let me bring back a theme from earlier. Chemistry plus polarization plus dynamics equals 3 keys. Any 2 won't open the vault. Chemistry tells you what it's made of and hints at formation environment. Polarization tells you about dust and processing. Dynamics tell you where it's been. Ideally, all three converge on a consistent story. For 3I, chemistry is weird but suggestive. Polarization is weird but explicable. Dynamics are untraceable. 2 out of 3 keys are in hand, but the third is rusted shut. So we're left with a partial picture, a sketch, not a portrait. Here's the emotional beat. And I don't shy away from emotion because science is done by humans who feel things. Atlas is a messenger from 3 to 11 billion years ago. It has travelled farther and longer than any human artifact ever will. It has seen more stars, more nebulae, more supernovae than we can count. It carries the chemistry of a world we'll never visit, a system we'll never map, a history we can't retrieve. And that's humbling, not defeating, not nihilistic, humbling. It reminds us that the universe is larger, older, and more complex than our datasets can capture. And that's okay. Limits are not failures, they're horizons. They tell you where to look next. So we've traced Atlas as far back as we can. We've analysed its coma, its dust, its motion. We've entertained wild ideas and dismissed some and kept others on the table. But the story doesn't end with analysis. The story ends where the object ends, leaving. Because Atlas didn't come here to stay. It came, it passed, and now it's heading back out into the dark. And what it leaves behind is not answers, but better questions. Part 15. The Infinite Drift. Let me paint you a picture. September 29th to 30th, 2025. 3I Atlas passes Mars at about 29 to 30 million kilometres. Fleets of orbiters watch. Mars Express tilts its cameras. Maven records plasma interactions. Rovers on the surface try to catch a glimpse, though it's too faint to see with human eyes. Then, October 29th to 30th, perihelion. Closest approach to the Sun at about 1.36 to 1.4 astronomical units. Solar heating peaks. Water ice, if it's buried, should start to sublimate. The CO2 to water ratio should shift. Non-gravitational acceleration might appear. Telescopes on Earth and in orbit watch every moment, and then Atlas curves outward, past Earth, past Mars again, out toward the asteroid belt, out toward Jupiter's orbit, and then, eventually, back into interstellar space. Let me recap the ground truth one more time, the facts we can stand on. No parent star traced. Perez-Couto ran 10 million years of integrations against millions of Gaia stars. 93 encounters flagged, 0 dynamically meaningful. The closest gave a velocity kick of 0.5 millimeter per second. Not enough. Not close. Carbon dioxide-rich coma. JWST measured a CO2 to water ratio of 7.6 plus or minus 0.3. Among the highest ever seen in any comet. Dominance at 3.3 AU, where water should be subdominant but not this subdominant. Extreme negative polarization. Minimum around negative 2.7% at 7 degrees phase angle. Inversion at 17 degrees. Unprecedented depth and narrowness. No analogue in solar system objects. No detected non-gravitational acceleration. Active coma, sunward asymmetry, but no measurable rocket effect in the orbit yet. Could change at perihelion. Nucleus size uncertain. Hubble upper limit about 5.6 kilometres. Could be as small as a few hundred metres. We don't know yet because the coma veils it. What might we still learn after perihelion? Whether water ramps up. If the CO2 to water ratio drops as the nucleus heats, that confirms thermal delay models. If it stays high, that confirms intrinsic composition models. Whether non-gravitational terms appear, A1 and A2 parameters in the orbit fit. If they show up and match water-jet asymmetry, natural comet physics wins. If they don't show up despite strong water activity, we're in puzzle territory. Whether the dust properties change, polarization at different phase angles post-perihelion, grain size distribution from brightness fall-off, spectroscopy for trace species if the signal-to-noise improves. There's a likely imaging window in mid-December 2025, best Earth distance geometry before Atlas dims and fades into the background stars. That's when we'll get the last good looks, high-resolution imaging. Maybe one more JWST pointing if time allows. Maybe radar attempts if it comes close enough, though that's unlikely. And then, silence. Atlas will be too faint, too far, moving too fast. It'll slip below detection limits, and we'll be left with the data we have and the questions we couldn't answer. Put yourself in the timeline for a second. We're living through the discovery and characterization of only the third confirmed interstellar object ever found. 50 years ago, we didn't even know interstellar objects existed. 20 years ago, we had theoretical predictions but no detections. 10 years ago, we had Oumuamua and more questions than answers. 5 years ago, we had Borisov and a sense that maybe interstellar comets are normal. Now we have 3i, and it's anything but normal. We're watching history unfold in real time. Data drops, papers get posted to Archive, press releases go live, and in a few months it'll be over. Atlas will be gone, and we'll move on to the next one. But here's the frame I want to leave you with. The originless frame. Maybe origin stories have half-lives in a dynamic galaxy. Maybe by the time we encounter some travelers, their stories are blurred beyond recall. Not because they're hiding them, but because the galaxy is old and chaotic and information doesn't survive forever. Maybe the universe is full of orphans, not because they were abandoned, but because 10 million years is a long time and catalogues are incomplete, and entropy always wins. Let me float one final what if, clearly labelled as reflection, not claim. What if some things in the cosmos aren't meant to be traced but sampled? What if the right question isn't where did you come from, but what are you made of? What if interstellar objects are the galaxy's way of sharing chemistry across light years, mixing materials between systems that will never meet? Not messages, not probes, just materials. Dust and ice and carbon and water, drifting for billions of years, landing in random solar systems, seeding planets, or escaping, or getting caught by telescopes run by curious apes. What if Atlas isn't hiding its past? What if we lost it? Here's the voiceover line I want to linger on as the screen fades. Maybe 3i Atlas didn't lose its past. Maybe we did. Maybe the Milky Way is an ocean and Atlas is a bottle and the tide has been running for 10 million years. The bottle is real. The ocean is real. But the shore it launched from? That's gone. Washed away. Smoothed over. Lost to the infinite drift.